Hello everyone, my name is Trevor with SkyCiv, and today we're going to be talking about column buckling. Members that are experiencing high compressive stresses can undergo a failure mode known as buckling, which is a sudden sideways deflection and an overall loss in stability. Members that usually undergo buckling or are susceptible to buckling are columns because they're the ones that are experiencing high axial forces and compression. So if we wanted to kind of show this, I have a ruler here. We can imagine that with this ruler, if we have it supported on two ends and we're pushing down on it, it's not going to be yielding in the compressive direction. It's not yielding or crunching or crushing this way. But if we put enough force on it, it has a tendency to buckle out like that. And I'm putting a little more force on it. There we go. So that is buckling. That's where it's deflecting to the side suddenly and it's losing its stability. If I put any more force in it, then I would break it. So what is this force indicated by? You've probably seen this equation before, but this is the Euler's formula. So this force that's making it buckle is the critical buckling stress here. So this critical buckling stress is depicted by this equation, and we can see that it is equal to pi squared times E times I divided by the entity of K times L squared. So if we go through the terms here, pi is constant, E is constant, I is constant. E is going to depend on the material that you're using, and I is going to depend on the actual section of your member. So whatever the W shape is or whatever the shape is, it's going to have a specific moment of inertia in the axis or against the axis that's going to be analyzed for buckling. And if you come down here, we have K. We'll talk about that in a second. And then we have L. L is going to be the unbraced length of the member. So the main thing we see here is this is the only thing that can really vary for a specific member, and that it's powered to, it's a powered term. So for example, if you increase the length by 4, you're actually going to be decreasing your critical stress if you increase your length by 2, you're decreasing your critical strength by 4 because this is a squared term. So this has a big impact on what your critical stress is going to be for buckling. So what is K? K is dependent on the actual boundary conditions of your column. So for example, we have 3 very common situations here. And again, K is just an arbitrary constant number here. And again, it depends on the boundary conditions. So if we look at a pinned connection, so imagine this is our column. We have pinned at the top, pinned at the bottom, and then this is our deflected shape. We know that for the 2 pin locations, it's going to allow our member to rotate. That's what a pin release means. So it's stiff at the top and the bottom, but it's not as stiff as maybe this condition. So it's going to be able to kind of bow out at the top and bottom, and it's going to be a little more susceptible to buckling than, say, this condition. And what we can tell, obviously, is that the higher the K value, the more susceptible it is to buckling, the lower this will be. So again, if we think about it intuitively, here's our K equals 1. This is for the pin-pin connection. If we look at the the fixed connection, the fixed connection or the fixed end conditions, they're telling us that there's 0 rotation at those 2 ends. So that the unbraced length of this, or the point where it's going to start deflecting out or bowing out, is further along the member. So we can say that it's 0.5, K equals 0.5, so it's less susceptible. And then lastly, on the other end, if you have a cantilever like this, a vertical cantilever, the stiffness at the top is basically non-existent because it's free. So if you imagine if this was here and I just push this, it's going to deflect a lot easier than it would be in this case. So that is where we get this K equals 2.0. And this can be empirically derived, but here is just some common. So what does that mean in relation to yielding or actual compressive, compression yielding? Well, we can move over here. First thing we want to talk about is the slenderness ratio. The slenderness ratio basically describes how slender a member is. So it's depicted by this lambda here, and the equation to find the slenderness ratio is KL over R. K is going to be the same K based on our boundary conditions of our member. And then L again is going to be the unbraced length. And R is the radius of gyration in the direction that is being analyzed for buckling. So it's kind of similar to I, but it's basically just a measure of how stiff it is in that direction. So we can see that, again, as a member gets longer, the section is a little thinner, it's not as thick. This is going to go up, and conversely, for the other case, it's going to go down. And if we look at this graph here, now we're looking at the maximum compressive theoretical graph. So on the x-axis here we have slenderness ratio, and that's depicted up here. On the y-axis we have the critical stress for compressive or axial failure. And we have Fy here. This is our constant yielding stress. And actually what we'll do is we'll just start at 0. If we imagine a column that's very short, very stocky, very sturdy, so a very, very low slenderness ratio, it's not going to buckle. So as we increase the stress on it, it's going to get to a point where Fy is going to be equal to the stress that it's seeing in the compressive direction, and it's going to yield compressively, or in a compressive failure mode, and it's going to plastically yield. So if you imagine, again, a super short structure, you push on it, there's no way it's going to buckle. If I take my ruler here and I try to make it really short and try to buckle it, it's not going to happen. The first thing that's going to happen is it's going to get crushed by the force that I'm pushing on it. And that's what's happening here. And as we move along our x-axis here, our member is getting longer, it's getting more slender. Now if we increase the load, it's going to touch the Euler curve here. This is the depiction of basically this equation in stress versus slenderness ratio. And because we have this square term here, what's happening is we're getting a parabolic type shape of the curve. So on this end, very, very slender. If we increase the force, it's going to buckle. And if we stay underneath this curve and underneath the yield curve, this is all elastic behavior. So this is where it would maybe deflect a little bit. But if you go outside of this, or you increase it at all outside of this range, this is where it's plastically deforming. This is where you're going to get actual inelastic behavior, and it's going to deflect and deform where it's not going to go back to its original shape. So this is kind of just how we can describe how buckling is interacting with compression, because they work kind of synonymously here. So that's just a little bit about buckling and a little bit about how it interacts with not only the itself in a graph, but also with the yield strength. So up to this point, we've discussed buckling in terms of a single member, but how do we incorporate that into the analysis of an entire structure? We can't really go through and analyze every single member for buckling because it doesn't really take into account the stability or the stiffness of the entire structure. It's actually common in structural analysis software to use a rational elastic buckling analysis via an eigenvalue analysis. And what this is basically going to do is going to evaluate the entire structure as a whole, groups of members and individual members for buckling. We want to use this type of analysis because part of a structure could be buckling without an individual member buckling. So for example, if we have a 2D truss or something like that, all of the members are going to be pinned together, and there might not be a single member that's buckling out of plane, but the whole truss itself might be buckling in and out of plane, or a group of members might be buckling in and out of plane. And that's where the eigenvalue analysis comes into play. Euler's formula here was actually derived by an eigenvalue analysis. So in general, if you wanted to analyze your structure for buckling, the eigenvalue analysis is going to be the best bet. It's going to be the most accurate. Make sure to look out for a full video on eigenvalues and eigenvalue analysis if you want to learn more in-depth information about that topic. If you guys like this video, please subscribe to our YouTube channel and make sure to follow us on LinkedIn and Facebook, and we hope to see you on the platform soon.